Okay, so on to question 2. Right, the first question here was generally done pretty well. Excuse my scribblings here. Decided to write out the answers to make it a bit quicker going through, as largely this was done pretty well. You should all be able and very comfortable drawing Maxwell-Boltzmann diagrams. Quite a few people forgot to label the axes. I probably taught you, I think, the number of particles go on the vertical axis here. The exam board prefer fraction of particles. Both are given the mark, so I've left it as the way I would have taught you. An energy or kinetic energy on the horizontal axis. A Maxwell-Boltzmann distribution shows you the number of particles, or if you like, the fraction of particles that have each particular amount of energy. So there's very, very few particles with no energy at all, and there's very, very few particles with lots and lots of energy, and most particles have this kind of middling amount of energy. And we learned how that graph shifts if you increase temperature. That's not what this question was about. That's something you should know as well, a very common question on that. The curve, you need to know, starts at 0, 0, starts at the origin, goes up and then down, doesn't touch the horizontal axis again. It should just shallow out. And somewhere on that downward curve, doesn't really matter where, you should have the activation energy of the uncatalyzed reaction labelled. And all of the particles, you didn't get any marks for shading, but all of the particles with energy more than the activation energy will have sufficient energy to react. They'll have energy greater than the activation energy so the reaction can proceed. If you chuck in a catalyst, you know that the activation energy decreases, so it must shift to the left here. And that means a greater proportion of the particles would be would have energy greater than the activation energy, which is why catalysts increase rates of reaction. You get a mark for getting the axes labelled correctly, you get a mark for the correct shape of the curve, and you get a mark for labelling these two correctly. This question was done very well. I'm not going to spend time on this, very much time on this either. What happens if you've got the same mass of crushed calcium carbonate, crushed being the key thing instead of lumps? Clearly you've got a higher surface area if it's crushed. If you've got higher surface area, you get a faster rate, as you know from GCSE, which means you get a steeper curve. Everything else is the same, so you're going to get the same volume of gas. So the curve ends up at the same place as the dotted line provided by the exam board on their picture. So pretty straightforward questions there, which most people did well on, I have to say. Also, you did okay here as well, because what would happen if you had ethanoic acid instead of hydrochloric acid? And I think all of you know that ethanoic acid is a weaker acid than hydrochloric acid. And if it's a weaker acid, it is only partially dissociated, and that's what it's really looking for the mark. You could have said that you get a lower concentration of H+, because of course concentration is related to rate of reaction. But most people said that, and that means the rate's going to be slower. Okay, so slower reaction rate, or you could just say the rate decreases. I thought question C here, 2C, was quite tricky to answer. They gave a few options in the mark scheme. The way that I quite like to answer it, I would say, would be that if you're using hydrogen ion concentrations, they range from 1 times 10 to the minus 14, roughly, up to about 1 mole per litre. So it's a huge, huge range of numbers. You've got to use these very tiny numbers. You couldn't simply say that these numbers are hard to work with, because anybody with a calculator who knows what they're doing can use them. But you could say that if you use a pH scale, a logarithmic scale, it's simpler, it's a simple scale. Or what some of you did, and I quite like this too, was said that the hydrogen ion concentrations are easier to compare if you use a simple pH scale. So that would have got the mark there. Not the easiest question, I thought. We did okay on that, largely. This question's a bit more challenging. This is, I know you did this in class using the new pH meters. You had a look at one of these titration curves, I think, using a weak acid and titrating with a strong alkali. So if you've got a weak acid, I'll just take my time actually. So the graph, you've got a titration with 25 centimeters cubed of 0.1 molar ethanoic acid. So you start with ethanoic acid with a pH of around 3, and you're titrating with very similar concentration, the same concentration, but a strong alkali. Okay, so you're expecting the pH to start at about 3 and eventually end up at 12 or 13, thereabouts, okay? Because you've got a strong alkali there. Now, this first region of the graph here, you get this little sharp bit at the start, which I'm not going to worry too much about, but this big region here is called the buffer region, okay? So it's a good idea to be aware of what's happening in that buffer region there. And that's at the point where you haven't yet got to neutralization point. I think you know at B, you've got to neutralization point. You've used up all the ethanoic acid with the sodium hydroxide you're adding, okay? So B is pretty straightforward. That's the end point of the reaction, or the neutralization point. But at A, we haven't completely neutralized the acid yet. So we've still got some acid in there, still got some ethanoic acid. So you have to work out the species other than water and sodium ions that are present at A and B. So you've still got some ethanoic acid in there, but you also, of course, given that some of the ethanoic acid has reacted with sodium hydroxide, you would have some ethanoate ions as well. You needed both of those for the first mark. And at B, all of the ethanoic acid has been used up, so we've only got ethanoate ions there. And it might be helpful to just draw the balanced equation. So we've got CH3COOH plus NaOH. So at point B, that reaction has gone to completion. Oops, plus H2O. I think what sometimes people think is that the end of the reaction is here. The reaction is complete at the equivalence point there at B. Okay, so we've only got the ethanoate ions left, plus sodium ions, plus water. Okay, and you get a mark for that. A lot of people got this mark. Very few people got this mark. 2 marks in total there. This question was done extremely well. Nearly everybody got 2.88 for that one, so I'm not going to spend too long on it. You know how to turn Ka into hydrogen ion concentration using this equation and converting that to pH. So really, I'm not going to dwell on that at all. Absolutely standard stuff, which you did very well on. Okay. Over the page, a little bit more tricky, a little bit more challenging, I thought. But why is sodium ethanoate basic? And if something is basic, essentially you've got to think, okay, well, somehow it's going to generate hydroxide ions in solution. So how's it going to get them? So what happens is this reaction. This reaction is in equilibrium, and you've got a little bit of sodium ethanoate in there, or ethanoate ions. They will react with water, and in doing so, they'll take a hydrogen ion from the water, leaving behind a hydroxide ion there. Okay, so you needed to know that reaction. You need to know why, in titrations like the one that you've just seen, this equivalence point has a pH above 7, and that's true for all weak acid, strong alkali titrations. The equivalence point is always going to be above 7. Okay. For the same reason, the salt at the equivalence point deprotonates water to a small extent. If you used ammonium, if you had an ammonium chloride solution, you're expected to know that ammonium is slightly acidic. Okay, it's acidic for a similar kind of reason. So it's acidic, so you say the pH is less than 7, which many of you got actually. Just as a little aside, do you know why it's acidic? Well, it's acidic because ammonium ions react with water. I should do this as an equilibrium as well. And that generates H3O plus or H plus and ammonia, and it's this stuff that makes the pH less than 7. Okay, but that's what you needed for the mark there. For part E, you struggled, but I know that you've covered this twice. Okay, I know you've covered it twice during the course. So formulate the equation for the reaction with nitrogen dioxide and water to form 2 acids. You've done this in the acids topic when you're learning about acid rain, and you also would have done it in the bonding topic as well, knowing that nitrogen oxides produce acid. So I know that you've seen it twice. Unfortunately, you have to learn this reaction, I would suggest. Okay, so 2 nitrogen dioxide plus water goes to HNO2, nitrous acid, and nitric acid, HNO3. And this reaction at the bottom, all you have to do is to know that nitric acid reacts with calcium carbonate to give calcium nitrate, water and carbon dioxide, something my year 7s, 8s and 9s should know. What you guys should know as well is that calcium is a 2+ ion. and that nitrate ions are 1 minus, of course, and so you need 2 of them to make calcium nitrate, and so you need to make sure to balance it. You've got 2 nitric acids plus 1 calcium carbonate goes to that plus that plus that. I think that's balanced. Okay, and that I think is all of question 2. So I'm going to pause again.